Now, let's start a fresh new topic, a very interesting topic, MOSFETs. Okay, um, let's start the idea of MOSFETs. Metal oxide semiconductor field effect transistor. So this is the basic building block of many semiconductor devices, of modern integrated circuits, iPhones, tablets, laptops, just about any semiconductor device, the microcontroller or the microprocessor that you can think of is built up using metal oxide semiconductor field effect transistors. Okay, it is very, very important that we understand the basics of MOSFET thoroughly. It can be confusing if you're going through this material for the first time. This can be a little daunting. Um, with all the complexities and all the higher order effects, so on and so forth. But we are going to take a very systematic walk through the theory of this semiconductor device, so we are in good shape. um, in in conjunction with Dr. Headley's videos and the informal introduction that I provide in this class, and the more formal uh, lecture that he provides in the recorded videos. Between these two, you should be in good shape in navigating this landscape of understanding MOSFETs comfortably. Okay, so as we will see, MOSFETs come in two flavors. There can be NMOS, N-channel MOSFETs, or there can be PMOS. Okay, I'll talk more about the underlying architecture again, but then there can be two kinds of flavors. There can be NMOS and PMOS. Okay, MOSFETs are the devices that are the building blocks um, of modern electronics. So we look at the regions of operation. There can be four regions of operation: cut off, which is turned off, triode, or saturation. Compare that with a diode. Diode had just two regions of operation, right? Forward biased, where it is on, and reverse biased, where it is off, right? This guy, the MOSFET, has three or four regions of operation. Now, MOSFET has four regions of operation of interest to us. Now, cutoff is pretty similar to the off of a diode, so that's least interesting part for us. But then we spend most of the time in saturation region, and then we also are interested in triode region. Okay, so we look at the different regions of operation for a MOSFET, then we look at the large signal analysis. Okay, we did the large signal analysis for a diode, right? When we look at the large signal analysis for a diode, we modeled it using two different models. One was the constant voltage drop model, and the other was an ideal diode model. Okay, where we model it as a short circuit. There's no voltage drop across this. In the constant voltage drop model, we model the diode as um, a battery with zero point 0.7 volts across it. Okay, the large signal model for a model. So similar to that, we look at the large signal model of a MOSFET. Okay, so we look at the large signal model of a MOSFET, then we incorporate channel length higher order effects, channel length modulation body effect, and then we look at the DC biasing, then the small signal model of MOSFETs. Does anybody remember the small signal model of a diode? If you remember the small signal model of a diode, we modeled the diode as a resistance. The argument was that if you look at the diode characteristics, it is exponential, all right? It's definitely exponential. But if you look at a small enough portion of um, the diode characteristics, the V, versus I characteristics. For that small portion, it's going to look like a straight line. Okay, it's going to look like a resistor. A linear relationship is a resistor, right? So the diode IV characteristics. So for the small signal analysis, we modeled the diode to be a resistance. Similarly, we look at the small signal model of a MOSFET as well. And then we look at the MOSFET as an amplifier, and then we summarize the important concepts. Okay, so let me reiterate what I discussed so far, or let me kind of give you a preview summary of MOSFETs before we even talk about MOSFETs. Okay, MOSFET is a semiconductor device that's a building block, and there are two flavors of it. And I'm going to introduce, as I am talking to you about the devices, I'm going to keep introducing interesting concepts like the symbol, like the number of terminals, so on and so forth. Okay, like the symbol for it, like the cross-section layout of it, so on and so forth. There are two flavors of MOSFETs. There is the N-channel MOSFET, and there is the P-channel MOSFET. Okay, the symbols are shown here with the arrow pointing out. Okay, and then for the N channel and the arrow pointing in for the P channel. Okay, so these are the symbols for the basic building blocks called MOSFETs. Okay, there are names to these terminals. One of them is called the drain. Okay, one of them is called the source. Okay, the other is called the gate. Okay, similarly, this guy is called the source. This guy is called the drain, and this guy is called the gate of the PMOS. Okay, PMOS channel, and I use these terms PMOS, okay, and NMOS interchangeably to mean N channel and P channel MOSFETs. Okay, how did they get the name called MOSFETs? Okay, when we look at the structure or the construction of a MOSFET, we will see that it is a sandwich. Okay, sandwich of metal, oxide, semiconductor. Okay, semiconductor. FET is field effect transistor. Okay, this is called metal oxide semiconductor field effect transistor. And once we look at the structure of the MOSFET, we will understand this. Okay, so let me show you some more details about this MOSFET. Let me show you another symbol for the NMOS. Okay, NMOS is fundamentally, if you think about a PN junction diode, it's a two-terminal device. There is the P type and the N type terminal, the P side and the N side, right? MOSFETs, on the other hand, may sometimes be shown using 3 terminals or sometimes be shown using 4 terminals. Okay, so here is the symbol. There is the drain shown using D. There is the gate. Okay, that's the floating gate. And there's the source of NMOS. Here is the source. Here is the gate. And here is the drain of a PMOS. Okay, this is exactly the same as this guy. Okay, this PMOS is another symbol for the PMOS over here. The NMOS shown here. Okay, here is another symbol for the same NMOS transistor. So the fourth terminal that is shown here is called the bulk or the body or the substrate. Okay, the bulk. Okay, for the PMOS transistor, the arrow is shown pointing out on the bulk. Okay, for the NMOS transistor, the arrow is shown pointing into the bulk. Okay, but the most often used symbols are these, the ones on the top. Okay, with the arrow pointing out on the source. for the NMOS with the arrow pointing in to the source for the PMOS. Okay, that's the idea. And then I'll show you one more symbol for NMOS transistor. That is a symbol for NMOS, and for the PMOS, it is shown with a bubble. Okay, so fundamentally, MOSFETs are 3 or 4 terminal devices. Okay, the terminals are source, drain, gate, and the fourth terminal, which is the bulk. Okay, the fourth terminal, which is the bulk.
Professor, like how
Yes,
can we compare these to the BJTs? Like, did we cover it?
we did not cover BJTs yet, but they're fundamentally different in the sense that this guy is a voltage controlled current source.
Okay.
Okay, BJT on the other hand is a current controlled current source. We'll talk about that later. Okay, for now, we'll just continue with the discussion on MOSFETs. I did not talk about the operation of MOSFETs yet. I simply introduced that it's a 4-terminal or a 3-terminal device, and it showed you the symbol for the MOSFETs. Okay, questions so far, please. Okay, so without going into the details of the structure of the MOSFET yet, I'm going to present to you more summary of a MOSFET. Okay, MOSFET slide number 2. We summarized the idea of a MOSFET, that it's a 3-terminal device, and showed you the symbols. It means metal, oxide, semiconductor. That's where the MOS comes from. Field effect transistor. That's where the FET comes from. Okay, I call them interchangeably NFET, NMOS, and channel MOSFET, so on and so forth. Okay, so summary of MOSFET: N channel, regions of operation. Okay, N channel, regions of operation. Okay, this is more or less the summary. This is what you will have learned at the end of the chapter. So all of this does not make sense yet 100%, but for now, let's start with the end in mind. Okay, so the MOSFET can have, broadly speaking, 2 regions of operation, and these 2 regions are further subdivided. Okay, it can be off or cut off, or it can be on, just like a diode that can be forward biased or reverse biased, right? So let me draw the symbol of an N-channel MOSFET here again. So I'm going to do that here. So there is the N-channel MOSFET. Okay, so there is the gate, there is the drain, and there shown with the arrow is the source. Okay, so this is the N-channel MOSFET. So let's see, depending on the terminal voltages, depending on the actual voltages on the terminals, VG. So the idea is VG, VB, VS, and V threshold. All of these voltages. So look at these are the terminal voltages. Voltages on the gate is called VG. The voltage on the source is Vs. The voltage on the drain is Vd. And the threshold voltage is called Vt. So they control the operation of MOSFET. So these control the region of operation. Okay, so I'm going to present to you a summarized view before getting lost in the details of how these terminals affect. Okay, so what is the condition for the MOSFET to be in cutoff region? For N-channel MOSFET, VGS less than V threshold. when the gate to source voltage, okay, when the voltage between the gate and source is less than the threshold voltage, then the MOSFET is turned off. Okay, when the MOSFET is on, it can be on in one of two regions of operation. Okay, it can be on in linear, or it can be on in saturation. Okay, it can be on in saturation region. Okay, it can be on in saturation region. Linear region is also called triode region.
Is VGS different than VG, Professor?
Yes, VGS is VG minus VS. Okay, so it is different from VG. Does that make sense? So in
Yeah.
other words, if VGS is 5 volts, if VG is 5 volts, VS is 3 volts, VG is 5, VGS is 5 minus VS 3, which is only 2 volts. So does that make sense? VGS is indeed different from VG. Okay, so let's see. This is also called triode region, unsaturated region, resistive region, so on and so forth. Okay, when VGS is less than V threshold, the MOSFET is off. Okay, when the VGS is less than V threshold, MOSFET is off. When VGS is greater than or equals to V threshold, then the MOSFET is on, and it can be on in one of two regions. Okay, which region it is on? Well, that really depends on VDS. VDS. If VDS value is greater than or equals to VGS minus V threshold, then it is on in saturation region. So for the MOSFET to be on in saturation region, VDS should be greater than or equals to VGS minus VT. If VDS is less than VGS minus V threshold, then the MOSFET is on in linear region. Okay, so that's the idea of MOSFET regions of operation.
Professor, like by listening to it, it seems to be like it is mostly used as a switch MOSFET.
It's used as a switch, it can be used as amplifier, it can be used as a resistor. There are a bunch of different applications for that, but um, it does come in handy as a switch. Okay, it can be used as a switch. As a matter of fact, we use it in a lot of digital circuits as a switch to build a lot of and NAND gate, NOR gate, so on, and other kind of CMOS logic operations. Okay, so it can be used as a switch. Other questions, please.
Is VDS equal to VD minus VS? Same like.
Yes, correct. So let me write it here. VGS equals to VG minus VS. VDS equals to VD minus VS. Okay. All right. So even before knowing anything at all about the region, about the operation of this MOSFET, we should be able to do some um, quick problems. I'll give you some math. Let's do some problems here. Okay. Let's say I give you the VD to be 5 volts. Okay. This is the drain. Here is the source to be 0 volts, the gate to be 3 volts. What can you tell me about this MOSFET? Is it on or is it off? If it is on, is it on in saturation or in linear region?
How do we tell what the threshold voltage is?
Thank you. I was waiting for somebody to point that out. Let's say the threshold voltage is given to be 1 volt.
So it seems to be on, right?
It seems to be on. Why is it on? You look at the value of VGS, which is VG minus Vs, that is equals to 3 volts. Now VGS is greater than V threshold, which is 1 volt, because 3 volts is greater than 1 volt. So it sure is on the right hand side, VGS greater than V threshold. So it is on. Correct. What else? Is it in linear region or is it in saturation now?
Yes.
Saturation.
It's in saturation. What?
So 5 is greater than.
Yeah, it looks, it is in saturation, right? VDS is greater.
What's the value of VDS? You're thinking in the right direction.
Five.
VDS is VD 5 volts minus Vs, that is equals to 5 volts. And now what's the value of VGS minus V threshold? That is VGS is 3 and the threshold value is 1. So VGS minus V threshold is 2 volts. So VDS is greater than VGS minus VTH. So I'm here, VDS is greater than VGS minus VTH. So this condition is satisfied. Therefore, I am in a saturation region of operation. Does that make sense? So we'll do one more problem. So this is in saturation region. Let's do one more problem. It's fun. Why don't we do one more problem?
So when we say, Professor, VG or VD or VS, are these the voltages that we apply, like the bias voltages?
Correct. Correct. These are the external terminal voltages that we can apply. Okay, drain, gate, source. So if I were to take a voltage source and apply some voltage here, that would become my VG. Does that make sense?
Yes.
So let me give you a value of VD equals to 3 volts. Okay, VG equals to 3 volts. Vs equals to 1 volt. And V threshold equals to 1 volt. Okay, what can you tell me about this MOSFET's region of operation?
First of all, it's on.
It seems to be off.
It seems to be on or off?
Off.
Off? Let's see.
On.
Why would it be off?
No, wait, 1 second. No, it's on. Sorry.
It's on.
VGS is greater than VD.
So the first thing we want to do is we want to look at VGS. VGS is VG minus Vs, that is 2 volts. So compare this VGS with V threshold, which is given to be 1 volt. VGS 2 volts is greater than V threshold. This is V threshold, right? So the MOSFET is on. Correct? Now, so the MOSFET is on. So the next step, so that's the first step. The second step, once the MOSFET is on, you have to ask the question, is it in saturation or is it in linear?
It seems to be in saturation.
It seems to be in saturation. Why?
Because they both are equal. VDS and VGS
What's the
minus
value of VDS?
2 volts.
VDS is VD, which is 3 volts, minus Vs, which is 1 volt. That gives me 2 volts. What's the other side of the equation? VGS minus VTH. VGS is what?
Zero. Zero.
VGS is 1 volt, right?
Minus 1, 0
Minus
volts.
VTH is 1 volt. So all of this VGS minus VTH, all of
Is
this equals to 0. Okay, so
saturation
VDS, this guy,
is greater.
is greater than that guy. Okay, this guy is greater than that guy. So it is in saturation region. Does that make sense?
Yes.
Okay, we'll do one more example, shall we?
Yes.
Okay, we'll do one more example. Okay, so I'm going to erase all of this. Okay, let's say we'll still have the NMOS transistor. VD equals to 1.2 volts. Okay, VG equals to 1.2 volts. VS equals to 0.8 volts, and VTH equals to 0.5 volts. So what is the region of operation for this MOSFET?
It's off.
It's off, thank you, because the very first step is we look at VGS, VG minus VS 0.8, compare that to V threshold, which is 0.5, okay? On the left-hand side, I have 0.4, this guy is 0.5. So VGS is less than V threshold, which is this guy. Okay, when VGS is less than V threshold, the MOSFET is off. Okay, so this is for N-channel MOSFET transistor. Okay, so we don't even have to worry about if it is in linear region or saturation region now. Once it's off, it's not interesting at all. It cannot be linear or saturation. Only when it is on do we think of it being in linear or saturation region. So does that make sense? So the first thing, the first stumbling block is to make sense of all of these terminal voltages, VG, VD, VS, and of course the threshold voltage. So I hope we are able to get that hurdle out of the way before we muddle ourselves looking at the internal operation of the circuit. Okay, so when you want to think of the operation for p-channel region, that's a slightly different phenomenon. Okay, p-channel. So far we have been doing for n-channel, right? So for a p-channel MOSFET, okay, for a p-channel MOSFET, and I'm not going to go into too many details of this. I'll just tell you how to think about it. Okay, for a p-channel MOSFET, the polarity is reversed. Okay, VSG should be greater than or equals to VTP. Okay, so VTP is always negative. VTHN. Okay, VTH. When I say VTH, I meant VTH for the N-channel MOSFET. Right? So it has a positive value. Remember, I kept giving you 0.5, 1 volt, 2 volts, so on and so forth. VTH for N-channel MOSFET is positive. VTP for a P-channel MOSFET has a negative value. And I keep using VTP interchangeably with VTHP. What I mean really is the threshold voltage. The threshold voltage of a PMOS is a negative value. So we almost always look at the magnitude of that. So the magnitude is a positive value. Okay. So For a p-channel MOSFET, everything is the equations are almost very similar, except that the polarity is reversed. So in order to understand whether the PMOS is on or off, and when it is on, when you want to look at the region of operation, is it in saturation or is it in linear region? A clean technique is to use VGS greater than or equals to VTH. The same equations as you would use for NMOS, except put everything in magnitude. The magnitude of VGS should be greater than VTHP, okay? And then it's kind of, it'll get you there. Sometimes it may not get you there. So once that is true, VDS greater than or equals to VGS minus VTHP. So put everything in magnitude, okay? That will give you the, if you look at the magnitude of this guy, if this is the case, then you know for a fact that the NMOS transistor is in, the PMOS transistor is in saturation region, okay? If it is less than that, then it is in linear region, okay? For the off, that's still VSG should be greater than. The real expression is VSG should be greater than mod VTP. But then if you look at the magnitude of this, that will give you a quick view of whether it is on or not. So we look at that. We look at the PMOS a little bit more later. This is just a preview of what to expect for PMOS. So for now, don't worry too much about PMOS. Remember the NMOS. Okay, for the NMOS, the only conditions that you want to check are VGS greater than V threshold, greater than or equals to, then the MOSFET is on. When it is on, now you look at the VDS. Is the VDS less than VGS minus VTH, or is the VDS greater than VGS minus VTH? Okay, that's the idea. Questions, please. Questions so far? Okay.
Is there any concept of depletion region in this?
Yes, there is, and I'm going to talk about that shortly.
Okay.
Okay, I'm going to talk about the operation, the underlying physics behind the operation that makes this possible. Okay. Other questions? So there is the PMOS operation, which is the opposite to NMOS. You can you can save yourself the problem by a lot of trouble by looking at the magnitude when it comes to the idea of PMOS. Okay. And as we spend more time with N-channel and P-channel transistors, I'll give you more and more techniques that help you make this judgment by observation. Okay. Other questions, please. So this is a 3-terminal device, sometimes also referred, it can also be a 4-terminal device. I have conveniently not shown the 4th terminal, the bulk terminal. Okay. I'll talk about that later. Okay. Now let me give you something. This VGS, this term VGS minus VTH is
One
sometimes,
question.
yes, I'll be with you in 1 second.
Okay.
This is referred to as V on, or it is referred to as overdrive voltage, VOV, overdrive. So all you want to remember is V on equals to VOV equals to VGS minus VTH. Okay, that's the definition. Yeah, what's your question now?
Is there any cutoff region to
Yes, the off is the cutoff region. So when I say VGS is less than VTH, okay, in this condition, the MOSFET is cut off.
cutoff? It is known as cutoff.
Cutoff is the same as off. Okay, so the MOSFET region of operation, it can be on or off. When it is on, it can be on in linear or in saturation region. Okay. All right. So let's take a closer look at the MOSFET structure itself. Okay, and I'm going to draw a comparison just because we looked at the PN junction diode, and to show that this is exactly what we do for all the devices. We look at the underlying construction. Okay, just to drive home that point that this is not something new or alien that we are doing now. For the PN junction diode, we looked at the underlying structure that had PMOS and that had N-type region, okay, that are joined together, back to back, that are joined together at this junction, okay. That's the idea of PN junction diode. So we did, in fact, look at when it came to the idea of a PN junction diode, we looked at the symbol and we looked at the construction. That is exactly what we are doing here as well. Okay, so don't be thrown off. And there is a continuity here if we look at it. Okay, the symbol and then the underlying construction. That is exactly what we are doing here. Okay, here is the construction of N-channel MOSFET transistor. Okay, this guy, the large blue box that is surrounding this, that guy is called the body or the substrate. Okay, that's the substrate, and that's, remember, the fourth terminals that I sometimes show, that I don't show sometimes, bulk. Okay, this guy. So when you look at the N-channel MOSFET symbol that looks like this, okay, I said there are three terminals: gate, drain, and source, and sometimes there is a fourth terminal. I said there is a bulk, right? So that guy, that bulk, is this guy, the body, okay, is shown here. Okay, that's the P substrate. It's a P-type substrate. All of this, all of the shaded region is the body. Okay, that's the idea. That's the bulk. Now let's look at one of the other terminals, which is the gate here. The gate terminal. Oops, let me do this. The gate terminal, which corresponds to the gate terminal over here. Okay, that's the gate terminal. What you want to realize is the black region there is the metal. Okay, that's a metal. Okay, underlying that region, I have a silicon dioxide or an insulator. Okay, I have an oxide or an insulator. So this is an insulator region. So what is the current? What would be the current flowing into the gate if I have an insulator sitting between the metal and the underlying region? What would be the amount of current flowing in?
Insulator, so it will be 0.
It'll be 0 because there's a insulator sitting in between, right? There can't be any current flowing in here because it is separated by a layer of insulator, right? So there is a metal, okay? And then there is a layer of insulator, which is oxide, O-X-I-D-E, oxide. There is a metal. And underneath that oxide is the channel, which is the semiconductor.
So like that's why it is known as voltage controlled, because there is no current.
Yeah, part of the reason is that, yes. Okay, so there is, let's look at that is correct. You're right to begin with, yes. So here is the metal, oxide, semiconductor, hence the name MOS. Okay, there is a sandwich of oxide, between a metal layer and a semiconductor. What's the semiconductor type? It's a p-type semiconductor. Does that make sense? So that's the metal oxide and the underlying blue region, which is semiconductor. Okay, now let's take another closer look. Let's take some more closer look. Look at this n-type region here. Okay, that's connected to the terminal over there. So there is a highly doped, if you look at it closely, it is N plus. What does it mean? It simply means that it is a N-type doping, and the plus here means that it is heavily doped. A heavily doped N-type region, okay, that acts as a source, okay, that corresponds to the terminal here. That's the source terminal in the symbol. Okay, corresponding to that, there is a heavily doped, there's another N plus region over here, N plus, heavily doped N-type region, right? This is a heavily doped N-type region, and this corresponds to the drain terminal over here. Does that make sense? So this is the symbol of a MOSFET side view, okay? If cross-section view, if I were to cut it like so, if I were to slice it from the top to bottom like so, I'll find this. But if I were to have a top view of it, then I would have a gate followed by a source followed by a drain. So let me highlight those areas here. So the drain is this guy that's shown in red. Okay, the gate, the purple region, is shown here. Okay, that's shown like that. And then there's a green region, which is the source, which extends through all of this. Then there's the drain, which extends through all of this. Then there is the bulk, okay, the underlying bulk, all of that, okay, which represents the fourth terminal. So that's the relationship between the top view, the side view, and the symbol view, okay, of a MOSFET. It's easy, the MOSFET, as confusing as some people find it to be, it becomes easy if we go through understanding it in a methodical way. Okay, so questions so far, please. All right, so there are certain dimensions that are of interest to me here. Okay.
Oh, sorry, I had a question, Professor.
Yes.
So, if the source and the drain are both N-type, then doesn't that mean they're both like super heavy in electrons? So why would current flow that way, I guess, if they're kind of the same thing? That's my question.
Yes, the question is, that's a very good question. That goes to the fundamental operation of the MOSFET actually, okay? There is N-channel MOSFET sitting there is N-channel source sitting all the way to the left, and there is N heavily doped drain sitting all the way to the right. So the source is right here, the drain is right here. Why is there no current flowing between them? Well, there is no current flowing between them because look at this area. They're separated by a P region. Okay, this N-type source and the N-type drain, they're separated in space by a P-type region, and that's the reason why there is no current flowing between them as of now. And we are going to do something about it to make current flow between them. Does that answer your question?
Kind of. So both the source and the drain are like negatively charged, I guess, because they're full of electrons, right?
They're full of electrons. They're not negatively charged. There is, if you remember, both the N-type and the P-type material are neutral because there are as many holes as there are electrons. But the electrons here are free, except that the holes are bound. Okay? So their net charge is neutral, but they have an abundance of free charge carriers, free electrons to move around. but there are equally number of holes, except that they are bound and they cannot move. Okay, so I'll answer your question in a different way. Your question is, why is there no current flow between source and drain, right?
Yep.
In order for a current to flow from one point, from one node A to a node B, the prerequisite is that there should be a voltage between these two, right?
Right.
If there's a voltage difference between these two, then the current flows. But as of now, I have not set up any voltage difference between the source terminal and the drain terminal, right?
Right.
So there cannot be a current flow yet. Okay, so let's say I put a voltage of 5 volts here and a voltage of 3 volts here. Can there be a current flow yet? Well, no, because they're still not connected. If I were to establish a connection between them and establish a voltage difference between the two, then the current flows. Okay, and I'll talk about that in a more detailed explanation shortly. For now, please bear with me that they're separated in space. As of now, the source is physically separated from the drain, so there cannot be any current flow. And even if there was a connection between the two, I have to establish a proper polarity between them. So two conditions need to happen for the current flow.
Okay. Thank you.
Yeah. Other questions, please. All right. So let me see if I got everything on this page. Metal, oxide, semiconductor, field effect transistor. That's the idea of MOSFET, because it's a sandwich of metal oxide semiconductor. It consists of a source on the left and drain on the right. Okay, and then a gate which controls the flow of current. Okay, there are two parameters that we want to pay attention to here. Okay, let me clear this up a little bit. The distance between the source and the drain. Okay, the distance between source and drain is called the length. It is an important parameter for me. Also, when I'm looking at the three-dimensional view, this guy, okay, this dimension, that's the width of the MOSFET. Okay, this guy is the length of the MOSFET. Okay, the physical separation, the distance between the drain and the source, that guy, the length, the distance between those two is called the length, and the dimension going into the plane of the paper, that's not shown in the view on the right hand side, that's width. Okay, it turns out that this width and L are important design parameters when it comes to the current flow of a MOSFET. Okay, all right. Let's see. So the width and length of the MOSFET are important design parameters. So that's good. So far we looked at the structure of the MOSFET. Okay, let's see if we can look at the operation of a MOSFET. Let me see. So here we are going forwards and backwards. I showed you the symbols for NMOS first with the symbol, with the source pointed, with the arrow pointed out, that's NMOS. Okay, with the arrow pointed in on the source terminal, that is PMOS. So in order to make certain concepts clear, we looked at the operation of with the symbols of the NMOS first. Okay, so let's look at the operation of PMOS transistor. Okay, of the NMOS transistor, sorry. Okay, NMOS transistor. Let me highlight the, let me show the symbol here again. Let's see. Here is the N-channel MOSFET. N-channel MOSFET. There is the gate terminal. Okay, there is the gate. That's the gate terminal. Then there is the drain. That's the drain. Then there is the source. Okay, source. That's the source. Okay, this is the source terminal. I'm not showing the bulk fourth terminal yet. Okay, to show that it's NMOS transistor, I'm going to point an arrow on the source terminal leaving the source. Okay, there are three terminals. How does this MOSFET work? Okay, to begin with, the source, okay, is physically separated from the drain. Okay, so there is no current flowing between the source and drain in that direction. The amount of current flowing is zero. Okay, the amount of current flowing is zero. Okay, so but if we want to turn the MOSFET on, so this is the gate, right? If we want to turn the MOSFET on, what we will do is to begin applying a positive voltage on the gate. Okay, when we apply a positive voltage on the gate, this acts like a capacitance and attracts electrons underneath the channel. Does that make sense? Okay, so if I apply more positive voltage, I have more electrons lining up underneath the gate. Now, once I hit enough positive voltage, once I apply enough positive voltage, once I have enough positive voltage, then what happens is there is enough electrons that line up. There is enough electrons that line up between the source and drain to form a continuous connection. Does that make sense? Questions, please. Okay, so the idea is when I keep applying the positive voltage, at some point there is going to be enough positive on the voltage on the top metal layer of the gate, enough plus signs on the gate to attract a continuous channel of electrons between the source and drain so as to make a continuous connection. Okay, now who can tell me if the MOSFET can conduct current or not? So the current is I drain to source. What is the amount of current flowing right now?
I think it should be 0
It's 0, and why would it be 0?
because there is no voltage on source and drain.
Thank you. There is no potential difference. Both of these, if you remember, are tied to ground. So there is absolutely no potential difference between these two terminals. So in order to make the current flow, what I'm going to do is to tie one of these, the drain, to a higher potential. Okay, I'm going to apply the drain to a higher potential. The drain, let's say I apply this to be 1 volt, and I still leave the source to be ground. Okay, so when I tie the drain to 1, what happens is these electrons, because there is a continuous connection between the source and drain, electrons begin to flow towards the positive drain terminal. Okay, so electrons begin to flow towards the positive drain terminal. So electrons are flowing in this direction. So the current is naturally flowing in the opposite direction. Conventional current is always opposite to the direction of the electrons. Okay, electrons begin to flow from the negative source terminal to the drain terminal. So there is a drain current, IDS, a current IDS that is not 0. Okay, the drain current IDS is not 0. Okay, so two conditions need to happen for the MOSFET to turn on and flow current. Okay, so let me say that one more time. Okay, when the gate voltage is tied to 0, okay, when the gate voltage is tied to ground, the source and drain terminals are all separated. Okay, the source and drain terminals are separated. So IDS is really 0 because there is no connection between the source and drain. But when I begin to apply a positive voltage on the gate, okay, the electrons begin to line up. Electrons begin to line up between the source and drain, corresponding to the positive voltage there. But they don't conduct yet because there is not enough positive charge. So at some point, I have to keep applying enough positive charge to line up enough electrons so that a continuous channel is formed. Okay, so there is n-type electrons here, there is n-type region over here, drain. Now, there is a continuous connection between the source and drain. Now, at this point, if I apply a positive voltage to the drain, then current can flow. Okay, electrons will flow in the opposite direction. Current will flow in the from source to drain. So two mechanisms need to happen for the MOSFET to turn on. Okay, now let me take a step to explain why we call this a MOSFET transistor. Okay, if you think about it carefully, what is turning the MOSFET on? The MOSFET is turned on by the fact that I am applying. Say that again.
Like by the gate voltage.
By the gate voltage, thank you. I'm applying a positive voltage on the gate. Electrons are beginning to line up here. Electrons are beginning to line up here. If I apply a higher gate voltage, okay, more electrons begin to line up. And then at some point, it's going to turn on. The MOSFET is going to turn on when I apply enough positive voltage on the gate. So in response to the field, electric field that is applied on the gate, the amount of current in the MOSFET is controlled. Okay, so that is the idea of field effect transistor. The electric field that is showing up on the gate, that controls the current flowing between the drain and source. Okay, and that's the reason why we call it field effect transistor. Okay, make sense? So now we should also understand the idea of V threshold here, V threshold. Okay, the V threshold here is not KT over Q. Okay, this is different. This is not the same as the thermal voltage we saw in the diode. This is the threshold voltage. Okay, so threshold voltage is, you remember I said when I keep applying a positive voltage, at some point when I have enough threshold voltage, when I have enough voltage on the gate, the channel is going to be continuous. Well, that's some point where there is a continuous channel, that value is called the threshold voltage. How much voltage do I have to apply on the gate so that there is a continuous channel between the source and drain? How much voltage do I have to apply on the gate so that the MOSFET turns on? Okay, that's called the threshold voltage. Does that make sense?
Yes.
Questions, please. What questions do you have at this point? Okay. Now I'm going to make another leap here. Not that big of a leap, it's just an observation. Okay. Pay attention to this region. Okay. The black area is the metal. The black area is the metal. The area shown in white. So, and underneath is the channel. Okay. So there is this blue highlighted area. Okay. that is full of electrons, negative charge. And then there is the red highlighted area on the top that is full of positive charge. Okay, if you think about it, what does this represent? Positive charge followed by an insulator followed by a negative charge. That's a capacitor right there, right? If you pay attention to the area in between, what is the area that's in between these two?
Channel.
The green area. The blue area is the channel, right?
The
That's the
green
channel that conducts between source and drain. That's the blue area.
oxide.
The oxide, the green area shown here is the oxide, or it's an insulator. Okay, so what we have is a bunch of positive voltages and a bunch of negative voltages, okay, negative charge, separated by an insulator. What is that if not a capacitance? That is the very definition of capacitance, right? So that's the idea that we are going to understand now. In response to a positive voltage, let's see, there are enough electrons underneath the channel. Okay, these positive charges and the negative charges are separated by an insulator, and that forms a parallel plate capacitance. Okay, that is the Lord God put a parallel plate capacitance into a MOSFET. Okay, this C oxide is defined as epsilon oxide by T oxide, and the capacitance of the gate. So this is, all of this region is the gate, right? That's the gate region. The capacitance in that gate is a function of the length of the MOSFET, the width of the MOSFET, and the oxide capacitance per unit area. Okay, C oxide is oxide cap per unit area. Okay, where epsilon oxide is the permittivity of silicon, 3.9 is the relative permittivity, epsilon naught is the absolute permittivity of free space, T oxide is the thickness of the oxide. So this guy, this dimension, very, very narrow, this dimension, okay, that guy is the T oxide. The thickness of the oxide is the thickness of this layer, insulating layer. Okay, so that's the T oxide. We can see the length. Okay, the length is shown here as well. That's the length of the gate, and then the width of the gate. In order to understand the width of the gate, we have to look at the three-dimensional view. That's the width of the gate. Okay, so that's the idea. So the capacitance that has been placed in there by nature, okay, that is inherent. The capacitance is inherent to a MOSFET. That is formed because of separation of charges, positive and negative charges, through an insulating layer. That's the insulating layer I'm talking about. Okay, that insulating layer separates positive and negative charges, which leads to a capacitance, which can be understood in terms of C oxide times width times L, okay, where C oxide is the oxide capacitance per unit area. Okay, questions, please. Questions so far? The parallel plate capacitance is shown in green over here. And then I talked about VOV, right? What's VOV? The overdrive voltage. I mentioned about it. Remember the definition for VOV I gave? It's also called V on.
Beyond, like at which it starts conducting.
Right here. Right here. Remember?
Yeah. So,
Overdrive voltage
so it's
is
the
defined
voltage.
as VGS minus VTH. Okay, that's all there is to V overdrive. V overdrive voltage, when you see it or when you see V on, all you have to remember is VGS minus VTH. Okay, that's the definition of V overdrive.
Uh, if we increase the voltage, will the depletion region decrease
If we increase the voltage
at the
on
gate?
the gate, okay, if we increase the voltage on the gate, okay, the number of electrons lining up here drastically increases, okay, and that increases the current.
Okay.
Does it make sense? And that's the reason why it's a voltage controlled current source. The amount of current that is flowing between drain and source can be controlled by looking at the amount of voltage that is applied on the gate. If I apply a higher potential on the gate, the amount of current flowing between the drain and source is going to be higher. So voltage controlled current source. Make sense?
Uh, so like if we keep increasing it, and so at one time, the like the electrons between and drain and source will stop transfer.
Yes, there are higher order effects that happen. Um, what is supposed to be a square dependence on VGS does not adhere to the square dependence anymore because of mobility degradation. We can look at the higher order effects later. But for now, in a very crude sense, in a big picture understanding, if we increase the amount of the gate voltage as VG goes up, the corresponding IDS goes up. That's the big picture we will stick to for now.
Professor, like how can you define saturation over here? Like what is the saturation thing?
I'll talk about saturation. When we increase the drain voltage considerably, what is supposed to be a straight line channel does not exist to be a straight line anymore. It begins to taper off, okay? And that leads to saturation. We'll talk about that, okay? For now, and we'll talk about that using this kind of layout. So for now, I don't want to get a little ahead of myself, okay, and confuse. Okay, but that's a good question. Hold on to that thought. It's an important discussion. We'll come back to talking about that. Okay. Questions, please. Questions so far. Okay. So what you should understand is when VGS is 0, meaning that when there is no potential applied on the gate, and there is absolutely no potential applied on the gate, what would be the current flowing between the source and drain?
Zero.
Thank you. It's 0 because there is no connection between source and drain. It acts as an open switch. Okay, a switch that is open. But when I apply enough positive voltage on the gate, it acts like a short circuit, a closed switch. Okay, all right. So that's the idea of field effect transistor. The electric field between the gate and channel, the electric field, the electric voltage on the gate controls the current flow. Okay. All right. Any questions before we move further? All right, so let's look at the PMOS operation here. The PMOS operation is pretty similar to the NMOS operation, okay? Pretty flipped, okay? Instead of a P substrate, I have N substrate to begin with. Earlier, I began with a P-type substrate, right? A lightly doped P-type substrate. Now, NMOS transistors are not fabricated on a P-type substrate, but they're rather fabricated on N-type material. Then I have a P plus region. See, P plus source and drain region. Okay, P plus source and drain region. Okay, now what I do is instead of applying a positive voltage on the gate, if I apply a positive voltage on the gate, that attracts electrons, and I cannot connect these p-type regions. So for me to be able to connect these p-type regions, I have to be able to attract holes. Okay, so in order for me to be able to attract a channel of holes, guess what voltage I should apply on the gate? I should apply a negative voltage on the gate. So that explains VTP being negative. Okay, VTP is negative because I have to apply a negative voltage on the gate so as to attract enough positive charge carriers between the P-type source and the P-type drain. Does that make sense? Okay. So owing to the fact, so this is called a P channel or PMOS because the channel is comprised of P-type charge carriers, holes, positive charge carriers. Earlier, the channel was comprised of N-type charge carriers, electrons. So the name N-channel MOSFET. Here I have a P-type channel, therefore it's a P-channel MOSFET, PMOS. Okay, pay attention to the fact that the gate is seeing a negative potential compared to the source or the drain. Okay, gate is less positive so that it has a net negative charge and it can attract a channel of holes. Okay, so PFETs use highly doped source and drain regions. Okay, let's see the drain regions, the source and drain regions that are highly doped. Okay, the P plus regions in there. Okay, both NMOS and PMOS operate the same way, but the doping types, the voltages and the currents are reversed. As you can see, VT is negative for the PMOS because I have to apply a negative voltage on the gate to attract an enough, strong enough, a continuous enough channel underneath the insulator. Make sense? Okay, when we fabricate both PMOS and NMOS, so take a look at this. The one on the left, let's see, the one on the left, that's N channel, right? All of that is style. Put that as, okay. All of that is NMOS. Think about it, NMOS. So there is a P substrate, that's the P substrate. There is N-type source region, N-type drain region, and then N-type electrons can line up when I apply a positive voltage. So that's a NMOS region. Okay, that's a NMOS transistor. Okay. Now look at the other side. Look at this guy. Okay, that guy. This happens to be a PMOS transistor because there is, if I can, oops, there is a N-type region, N-well, there is a P-type source region, there is a P-type drain region. So, and a p-type holes. So if I fabricate both PMOS and NMOS on the same wafer, okay, on the same wafer, I'm fabricating an NMOS transistor and a PMOS transistor as well. Then I call it a CMOS, a complementary metal oxide. Because I have both N channel and its complementary cousin P channel as well. Because I'm doing both NMOS and PMOS on the same wafer, I'm able to fabricate N channel and P channel. We call it complementary metal oxide. Does that make sense? So what we do, the clever technique is P-type body is available to N channel, but P transistors need N-type body. Remember, P channels need N-type substrate. Okay, so in order to create a substrate for P channel, what we do is we dig a well of N-type material here. Okay, even on the P-type body substrate, we create a local well of N channel, N well. So this acts as the body or the bulk or the substrate for the P channel. Okay, a local well. So we dig a well of N-type, we dope that selected region with enough N-type material so that we can fabricate a PMOS in that region. Does that make sense? So modern processes use both NMOS and PMOS on a single integrated circuit. Okay, and that's the reason we call it a CMOS, complementary metal oxide semiconductor field effect transistor. Okay, now we have a very good understanding of all the little terms here. It's called a field effect transistor because the voltage or the field applied on the gate has an effect on the current. That's the field effect. It's called a metal oxide semiconductor because there's a sandwich here of oxide, metal, and semiconductor. And then it's called a CMOS, NMOS or PMOS, based on whether it is N channel or P channel or both on the same integrated circuit. Questions, please. Okay, now the next, let's see. So there are a lot of parasitic devices here. So questions so far, please.
Could we have, Professor, the other way around? Like we have a P body, could we have
Yeah.
an N body and then
Yeah.
go?
It is possible, in theory it is possible, but most process technologies, the fabrication clean rooms, typically it's convention to use a P-type body and N-well process. Okay, in theory it is possible to have the other way around. I can have N-type body and P-type well as well, but that's less often used. Okay, it's a good question. Other questions, please. Okay.
But what is the function of like SiO2 layer?
Yeah, it's just there to separate them. SiO2 is a good insulator. It's a thick silicon dioxide that separates any current that should not flow between these two. Okay, it keeps the current, it keeps unnecessary current going in the wrong direction. Okay,
so
there should not be any current flow between this guy and this guy unless you want it to flow. Okay, so this thick oxide separates interaction between the PMOS and the NMOS. Where it is necessary to be separated, we build a wall of silicon dioxide.
like what is the advantage of combining both PMOS and NMOS?
Or we can build very, very interesting circuits using CMOS logic, digital devices. We can get the advantage of both PMOS and NMOS. Okay, NMOS can provide good pull down, PMOS can provide good pull up, so we can get a very, very good, very well built robust logic circuits using both PMOS and NMOS on the same chip. Okay, NMOS is good at doing certain things, PMOS is doing good at certain things. So oftentimes we want to be able to use both flavors of devices in our circuits, and it's just a matter of getting that done. Designers want both PMOS and NMOS, so fabrication guys make it possible using this kind of CMOS logic, CMOS technology. Okay, that's a good question. Other questions, please.
So will the electrons branch from under the N plus region underneath the silicon dioxide to the N well? Is that how you get current flowing from one to the other?
There's only one way in which the current can flow here. If I apply enough positive voltage here, there's going to be current flow between the source and drain. Okay, remember the source, the current is going to flow, the electrons are going to flow in that direction, and then the current is going to be opposite. If I apply enough positive voltage here or enough negative voltage on the gate, there's going to be holes lining up here, and then there's going to be holes flowing in that direction. So the only acceptable current flow is between the source and drain of the NMOS and the source and drain of the PMOS.
It won't ever be between the NMOS and the PMOS though.
If you wanted to have a connection between the NMOS and PMOS, you cannot let that current flow in this direction. What you will do is you will make an external connection between this terminal here and that terminal here. That's the only acceptable path for current to flow. Okay, and this oxide makes ensures that there is no current flowing in any other direction. Okay, if you want connection between this NMOS and this PMOS, that's a very good question. What you will do is you will make an external connection between the two terminals. Make sense?
Yep.
All right, other questions, please. Very good. So let's continue here. What do you find anything interesting, or let me eliminate all of this. Okay. Now we know the idea of N region separated from another N region through P-type body, and how applying a positive voltage, applying a positive voltage on the gate. Okay, if I apply a really big positive voltage on the gate, that's going to connect the N-type regions. So far, so good. We are very clear in terms of the operation of the NMOS and PMOS transistors. Now, let's take a step back and see if we can recognize some devices that we already studied so far. Like diodes. Do you see some diodes here built in, even without my intention to want to build diodes? What is a diode after all? When a P region is adjoining another N region, that's a diode right there, right? So, yes.
Maybe a gate.
The gate, where is the PN over there? Well, notice an N region first. Where is an N region? There is N region. And look at the adjoining P-type body.
Oh,
This is P-type, right? All of this.
yes.
So you can think of this as a little diode between the P and N region. Okay. There is a diode. Okay, that's a diode right there. And similarly, and this is a diode I did not intend for it to be there. It just showed up. Okay, it just showed up because of the construction, because of the curious construction, because of the interesting construction of the MOSFET. There's another one over here, right? There is N region separating a P region. So there is, if you want me to write it out, there is N, there is a P, there is N, there is a P. There's a diode. I did not want for it to be there, but it showed up to the party anyways. Like so, similarly here as well. Okay, there is a P-type region separating an N-type region. That's a diode right there. Exactly the same here as well. So these diodes are called parasitic diodes. Okay, these diodes are parasitic diodes. Okay, style. Okay, these are called parasitic diodes because I didn't intend for them to be there, but they showed up anyways. Okay, these parasitic diodes, and we have to be very careful with them. We always want to reverse bias parasitic diodes. Okay, we want to reverse bias them because the only current flow that I ever want is between source and drain. Okay, that's the only current I want. Okay, I don't want any current flowing in the wrong direction. I don't want any current going between the drain to the body. Drain to body, I want it to be zero. So if I want this to be zero, I'm going to want to make sure that this diode, okay, right here is reverse biased. Okay, similarly, the same with all the diodes. All the parasitic diodes, I want them to be reverse biased and off because I don't want them to turn on in the wrong current flowing in the wrong direction. Okay, so in order to reverse bias this, I have to tie these N-type, these P-type regions to a negative potential compared to the N-type region over here. Similarly, I want to make sure that this N-type well is tied to the positive power supply, or the positive is more positive compared to the P region over there. So we'll talk about how to accomplish that. But for now, just notice that there are diodes all around everywhere that I didn't intend them to be, diodes that I didn't want there, but they showed up anyways. Okay, these are called parasitic diodes. Okay, so that's the idea that we're going to see here. FETs are really the devices being intentionally built. Correct. Field effect transistors are the devices that I'm intentionally building, but then there are just parasitic devices everywhere. Okay, parasitic devices are not desired, but they're present anyways. Okay, so CMOS designers must keep all PN junctions turned off or reverse biased. Okay, so there is a PN junction over here. There's another PN junction over here. Okay, so that's a N type. This is the P side of the diode. There is N side, there's a P side of the diode. So both of these P sides are tied to the bulk or the body or the substrate. All of these mean the same. Okay, the only way for me to reverse bias these diodes, I want to make sure that this bulk is tied to the most negative potential. Okay, the P substrate bulk is tied to the lowest potential, usually ground, and the N substrate bulk, because I have a P N diode, I want to make sure that this N region is tied to the most positive power supply, okay, so as to reverse bias the diode over there. Does that make sense? Okay, so that's the reason why I want to tie the P substrate to the lowest power supply and the N substrate to the highest power supply, so as to reverse bias these diodes over here. Okay, so that's the idea of CMOS feed effect transistors. Now the next few slides should be a breeze for us. Okay, this guy, the symbol of NMOS. Okay, there is the arrow pointing on the source, pointing out of the source. Okay, when there is, where there is an arrow, that's the source. If it is pointing out, then it is NMOS. If it is pointing in, then this guy is the source, and because it is pointing in, this is a PMOS. Okay, symbols for NMOS and PMOS transistors. Okay, we interchangeably use all of these symbols. Sometimes we only show 3 terminals, we don't show the 4th terminal, but it is there. All right, the 4th terminal, the body, the bulk, the substrate. The 4th terminal, it's also called the body, it's also called the bulk of the substrate. Okay, that's the 4th terminal, B. S is the source, D is the drain, G is the gate. Okay, questions, please. Okay, then we already looked at the regions of operation, right? So if VGS is less than VT, well, we know that already. VGS is greater than or equals to VT, the MOSFET is on. If the VGS is less than VT, then the MOSFET is off. Big deal. Okay, then there is, I didn't talk about the subthreshold region yet. I'll talk about that shortly. Okay, but then there is the triode or the linear region. Okay, when VDS is less than VGS minus VT. Okay, this guy, the V on, that's exactly the same as V on. That's exactly the same as V overdrive. Okay, VGS minus VT. Okay, there are many reasons why there are so many different names to the exact same term. Okay, they're slightly different in the application, but when you see this VGS minus VT, VDS less than VGS minus VT, that's the triode. When VDS greater than or equals to VGS minus VT, that's the saturation. Okay, so here is an approximation, like I said. VGS minus VT is VOV is VD sat. Okay, let me go back here. Let me show you this slide. This is much easier. Okay, so there are only two things that we want to remember. Let's look at the VGS minus VT. Based on the relative values of VGS and VT, we define if the MOSFET, we identify if the MOSFET is in off or on. Once we know it is on, then we look at VDS. If VDS less than VGS minus VT, it's in triode region or linear region. If it is in saturation region, then VDS greater than VGS minus VT. So VGS minus VT is nothing but VOV, V on, V saturation, so on and so forth. Okay, questions, please. Questions so far?
Like when we are in saturation region, then
Yes.
no electrons flow from drain to source, right?
When we are in off, no current, no electrons flow between drain and source. Okay.
And
When we are in saturation, there is some current flow.
okay.
Okay. So
And
there is some current flow in saturation region.
and when we are in active region,
Yeah, active region is usually triode region. Even then there is some current. The only time there is no current is in the cutoff region.
so what is the difference between active and saturation?
Yeah, active is usually in the context of BJTs. So for NMOS, we look at the triode and saturation. Active
Triode
comes
and
into the idea. Yeah,
So what is the difference between both?
I'll talk about it. In triode region, ID is usually a function of VGS and VDS in triode region. And in saturation region, ID in theory is just a function of VGS. Okay, so there are some differences. We can talk about that when we look at the ID VDS relationship. Okay, when we look at these equations, okay, ID, all of these equations, we'll talk about how these regions of operation differ. Okay, that's a good question. You're always one step ahead of me, which is a good thing. Hold on to that thought. We'll continue this shortly when we come back on Monday. Questions, please.